All right, well, today we're going to be continuing our definition of limits, specifically talking about one-sided limits. And the definition goes as follows. As x gets closer to c but remains less than c, the corresponding value of f of x gets closer to a number L. What this really means is that as you approach the limit, as you approach c from the left side of the graph. If we're talking about -2 and the graph is going this way, I'm only concerned about what is the graph doing as it approaches -2 from the left. It may be doing something completely different coming from the right, but I don't worry about that. If it has this negative sign kind of as a superscript for the value c, then we're talking about it coming from the left. There is a similar positive limit as x gets closer to c but remains greater than c, so you could think of that as it's coming in from the right. The corresponding value of f of x goes closer to r, some other number. Now, if the limit as x approaches c from the left of f of x equals a number L, and as the limit approaches c from the right approaches r, then we would say that the limit exists if and only if L equals r, meaning that these two numbers are the same. That's how you know the limit exists. Remember that it does not need, the point f of c does not need to exist. But as long as from the left and from the right, your graph is headed toward the same number, in this case L equals r, that's when we would say that the limit exists. Similarly, if you have two numbers that are the same, L and r, then the limit exists. Let's take a look at what this would look like in practice to evaluate a limit. This happens to be a piecewise function. Now, for the first piece, when x is less than 2, that's going to be a, because we're looking at the limit as x approaches 2 from the left, and that's what we have as our restriction on the domain in the piecewise function. So the limit as x approaches 2 from the left of 2x minus 1. That's the only part of the function I care about. And all of these, well, this is a constant, but there's no restrictions on the domain. So now we know that we can evaluate this limit by plugging in the value, because it will exist there. There's no break in the graph. And we get 3. And we can call that L. For part B, the limit as x approaches 2 from the right, we got to find where that happens on our graph, and that happens right here. So the piece of the piecewise function we're going to use is the x minus 2 piece. And again, there's no break in the graph, so I can evaluate that. Coming from the right, 2 minus 2 is 0. That's r. Therefore, we know, according to the definition, that L does not equal r, so we can make the general statement that the limit as x approaches 2. So that's the general statement. This is from the left. This one's from the right. But the general limit statement as x approaches 2, which considers both sides of this function, does not exist because L is not equal to r. They need to be headed to the same place. The other part of limits we're going to talk about today is continuity. And there's a three-prong definition to discuss a function as continuous at a particular point C. So it could be continuous a lot of different places, but maybe not at all points in the domain. The first, f is defined at C, so it has to exist and so it's in the domain of f. This is some number. Now we're going to add to that the two partial limits from the left and from the right that we just talked about. That's this guy here and this guy here. So if the limit as x approaches c from the left of the function f of x equals f of c, and that same function from the right equals f of c, then we can say a function is continuous at c. Okay, so these two statements, 2 and 3, remember, if they're equal, they create the limit statement, and that's what we just talked about. And if that limit as x approaches c of f of x equals f of c, meaning graphically, if from the left it's going to some point, and from the right it's going to some point, and it exists at that point, this is what we would say is continuous. Had that point been somewhere else, so even though the limit exists, but the point was somewhere else, all of a sudden it's not continuous. Think of it as you ought to be able to draw the graph without picking up your pencil. So determining the numbers at which a rational function is continuous, we've got this rational function here, r of x, and we will say determine the numbers at which the rational function r of x is continuous. So we just need to look for breaks in continuity, and we know that that tends to happen at asymptotes and holes. That's where we'd have to pick up our pencil. Otherwise, polynomials they're smooth, they're clean. So this guy by itself is a polynomial. There's no restriction on the domain. There's no restriction on the domain of x squared minus 6x plus 8 by itself. But the fact that it's in the denominator of this rational function means we've got problems. So looking at r of x could be rewritten as x minus 2 over x minus 2, x minus 4. So hopefully you're recognizing that it's continuous at all real numbers, but not at 2 nor at 4. We've either got a hole or an asymptote. And hopefully you're thinking to yourself, this guy right here, that's my hole, and this guy right here is my asymptote. And the reason that we know that is because those guys would cancel out. So not an asymptote, but still a restriction on the domain. So to get a better picture of what's happening here, we're going to evaluate the limit at the hole, because we know that the limit exists if there's a hole in the graph. Going back up here, the limit exists. It's headed to the same point. There just is a hole there. But an asymptote, that's not going to have a limit, because an asymptote's going in a different direction. The limit as x approaches 2, so we're saying as we go towards the hole, of what's now that we've cleared out the numerator, 1 over x minus 4. So again, that's because we were able to cancel out the x minus 2 factor. If I evaluate that limit, I get negative 1/2. So the hole, specifically, is at the point 2 comma negative 1/2. As we got closer and closer to 2, we're getting, for x, we're getting closer to negative 1/2 for y. Now, if we take the limit as x approaches 4, and in this case, as we're approaching 4 from, we know that it's not going to work. So x minus 1 over x minus 4, I can't just plug in 4. I've got a problem there. So what I'm going to do is look at it and say, okay, from the left side, what is it doing? As I get closer and closer to 4 from the left, where is this thing headed? And if I plug in -10, -8, -6, -5, -4.5, etc., this thing's taken off, getting closer and closer to negative infinity. It's going down as it approaches the asymptote. If I take a look at the limit as x approaches 4 from the right side of this same remaining r of x, and I plug in values like 10, 8, 6, 5, 4.5, and so on and so on, I'm ending up with the same value, only it's positive. So this is headed towards positive infinity. This confirms our asymptote, the fact that they're diverging as we get closer to 4. So a decent graph of this, and being generous with my term decent here, if I go 2, 4, 6, there we go, and then we'll go 2, 4, that's 1.5. So let me zoom in on this. -1/2, and that's 4, and then let's see, I'll put 2 up here because otherwise it's going to be in my way. We've got our asymptote at 4, and at 2.5 I've got my hole in the graph. There happens to be a horizontal asymptote at y equals 0, and otherwise we know that's going down to negative infinity as we approach from the left, and as we, say, approach from the right, that's going up to positive infinity. So we get like I said, a decent looking graph. We'll take a look at one more example, looking at where is this thing continuous, and because it's a piecewise function, the breaks are given to us. Each of these, right, a quadratic, a linear term, and a linear term, by themselves are surely continuous. However, there's a break at 0 and there's a break at 2. So we need to investigate what's happening at those critical values. So we'll take a look at the limit as x approaches 0 from the left. And when I approach from the left, it behaves like the first piece, x squared, and that's going to get me 0. If I take a look at the limit as x approaches 0 from the right, well, now that behaves like x plus 1, because I'm in this part of the domain here, and that's headed to 1. Since those two don't exist, they're not equal to each other, we have a point of discontinuity. It is not continuous there. The limit as x approaches 0 of f of x is not equal to f of 0. That is not true. Excuse me, I guess from the right side. It is true for the left side, but it's not true for the right side. And because these guys are headed in different places, it is not continuous at 0. Let's take a look at 2. The limit as x approaches 2 from the left still behaves according to x plus 1. We're still in that middle domain there. And I get 3 when I evaluate that. And the limit as x approaches 2 from the right side now behaves as 5 minus x, which also, if I plug in 2, equals 3. Now the last thing we want to check is f of 2 and make sure does f of 2 equal 3, and that is then the same as the limit coming from the right. So that does equal 3. Therefore it is continuous at 2, but it was not at 0. The existing domain of this function is from negative infinity to 5, so we would say it's continuous from negative infinity to 5 inclusive, comma, but not at x equals 0. So a couple examples discussing continuity, which, remember, has this three-pronged set of its definition, where it needs to be defined at the number and also approach that number from the left and from the right. The from the left and from the right was what we practiced at the beginning, the one-sided limits. So now you should be able to tackle the 14.3 worksheet dealing with one-sided limits and continuity.